Welcome to this coding tutorial. In this session, we will discuss LeetCode problem number 1051, titled Height Checker. We'll explore the problem requirements, analyze potential approaches, and work towards an efficient solution. Let's dive in. In the height checker problem, we are tasked with determining how many students are not in their correct positions when their heights are compared to a sorted version of the list. Imagine we have an array of integers where each number represents the height of a student. Our goal is to count how many heights in the original array differ from their positions in the sorted array. This number will represent how many students are standing out of order. The input to this problem is an integer array called heights, which can have a length between 1 and 100. Each height value in the array will also be a positive integer between 1 and 100. The output is a single integer, which represents the total count of mismatched positions. Essentially, we are comparing the original and sorted arrays index by index and counting the differences. Let's consider some examples to make this clearer. In the first example, the input array of heights is 1, 1, 4, 2, 1, 3. When we sort this array in non-decreasing order, we get 1, 1, 1, 2, 3, 4. Now, we compare the original array to the sorted array. At index 2, the original value is 4, but the sorted value at the same index is 1. At index 4, the original value is 1, whereas the sorted value is 3. And at index 5, the original value is 3, but the sorted value is 4. That gives us a total of 3 mismatched indices. Hence, the output is 3. In another example, the input array is 5, 1, 2, 3, 4. For the second example, the input array 5, 1, 2, 3, 4 sorts to 1, 2, 3, 4, 5. When we compare the two arrays, every index has a mismatched value. At index 0, for instance, the original value is 5, while the sorted value is 1, and this pattern continues for all indices. Since all 5 indices have mismatches, the output is 5. In the third example, the input array is 1, 2, 3, 4, 5. Here, the array is already sorted, so no indices have mismatched values. The output in this case is simply 0 because there are no students out of position. The problem also comes with a set of constraints and edge cases to consider. First, the length of the array, n, will always be between 1 and 100. Additionally, each height value in the array will always be a positive integer between 1 and 100. Some edge cases include scenarios where all elements in the array are identical. For instance, if the input array is 5, 5, 5, 5, the sorted array will be the same as the original, so the output would be 0. Another edge case is when the array is already sorted, like 1, 2, 3, 4, 5, which again results in an output of 0. Finally, if the array is in reverse order, such as 5, 4, 3, 2, 1, every index will have a mismatch, and the output will equal the length of the array. These constraints and edge cases help ensure that our solution is robust and handles all possible inputs correctly. To tackle the height checker problem, our goal is to identify how many students are not standing in their correct positions when the heights are sorted. This essentially means comparing the current order of heights with their correct, sorted order. One approach we could take is a brute force method, where we compare every student's height with all others to determine mismatches. The steps involve looping through all the students, comparing each height against every other height to find its sorted position, and counting the discrepancies. However, this approach has a time complexity of n squared, as it requires nested comparisons, making it inefficient for larger inputs. It's also worth noting that while this approach doesn't require additional space, the inefficiency of its quadratic runtime makes it impractical for real-world scenarios with larger datasets. A more efficient solution is to use the sort and compare approach. Instead of comparing each student with others repeatedly, we can first sort the list of heights to determine the correct order. With the sorted list as our reference, we can then directly compare each height in the original list with its corresponding value in the sorted list, counting the mismatches where they differ. The time complexity here is n log n, which is dominated by the sorting step, and the space complexity is n, due to the need for storing the sorted copy. This method is significantly faster than the brute force approach and is easier to implement, but it does require additional space for the sorted version of the list. This trade-off between time and space efficiency makes it a practical solution for most cases. Another viable option is the counting sort approach, which leverages the limited range of the heights, given as 1 to 100. This allows us to achieve linear time complexity. The steps involve creating a frequency array to count how many times each height occurs, using this frequency array to reconstruct the sorted list, and finally comparing the original list with this reconstructed sorted list to count mismatches. The time complexity here is O, n plus k, where k is the constant range of heights, and the space complexity is O, k, for the frequency array. This approach is faster than general-purpose sorting algorithms for large inputs and avoids the overhead of creating and sorting a copy of the list. However, its implementation is slightly more complex, which could make it less intuitive for some users, particularly for simpler problem constraints. For this problem, we selected the sort and compare approach due to its simplicity and balance between performance and readability. While the counting sort method is faster in theory, its additional implementation complexity doesn't provide a significant advantage given the small and constant range of heights. With the sort and compare method, we can quickly determine the target order by sorting the list, and the comparison step remains straightforward. The constraints of the problem, where heights are bounded between 1 and 100, ensure that the sorting step is efficient, and the trade-off between time and space complexity is reasonable. This strategy enables a clean and efficient implementation, making it well-suited for this particular problem while maintaining clarity for anyone reviewing or maintaining the solution. The problem, height checker, challenges us to determine how many students in a lineup are out of position when compared to where they would be if the lineup were sorted by height. We are given an array called heights, where each element represents a student's height. Our goal is to count the number of mismatches between the current order of the array and its sorted version. For instance, if the input array is 1, 1, 4, 2, 1, 3, the sorted array would be 1, 1, 1, 2, 3, 4. Comparing the two, we can see that there are mismatches at 3 indices. To solve this, the first step involves creating a sorted copy of the heights array to establish the correct order for comparison. Taking the example heights equals 1, 1, 4, 2, 1, 3, the sorted version is 1, 1, 1, 2, 3, 4. Next, we need to compare the original array with the sorted array. As we iterate through each index, we check if the current element in heights matches the corresponding element in the sorted array. For instance, at index 2, the original value is 4, but the sorted value is 1, indicating a mismatch. To keep track of such mismatches, we maintain a counter that increments whenever we find a discrepancy. For this example, mismatches occur at indices 2, 4, and 5, giving a total of 3 mismatches. Finally, we return this count as the result, which in this case is 3. Sorting the array is crucial because it provides a reference for the correct order of heights, allowing us to directly compare the current order with the expected one. This comparison process is efficient since both arrays have the same length. By iterating through the arrays once, we can count mismatches in O, n, time. It's also important to consider edge cases. If the input is already sorted, such as 1, 2, 3, the mismatch count will be 0 since no elements are out of position. Similarly, if all elements are equal, like 5, 5, 5, there are no mismatches. On the other hand, if the array is in reverse order, such as 5, 4, 3, 2, 1, every element will be out of place, and the mismatch count will equal the length of the array. These insights highlight the simplicity yet robustness of the approach. The algorithm primarily relies on 2 data structures. First, we use the input array heights as is. A sorted copy of this array is created to serve as the reference for comparison. Second, we use a simple integer counter to track the number of mismatches during the comparison process. Moving on to the complexity analysis, the time complexity is driven by 2 main operations: sorting the array, which takes O, n log n, and comparing the arrays, which takes O, n. Therefore, the overall time complexity is O, n log n. For space complexity, the sorted copy of the array requires O, n, additional space. Combining these, the total space complexity is O, n. The implementation of this algorithm is straightforward. First, we create the sorted version of the heights array. Then, we iterate through the original array, compare it with the sorted array, and count the mismatches. Finally, we return the mismatch count as the result. To better understand the algorithm, let's walk through an example. Given the input heights equals 1, 1, 4, 2, 1, 3, the first step is to sort the array, resulting in sorted underscore heights equals 1, 1, 1, 2, 3, 4. Next, we compare the two arrays, index by index. At index 0, both values are 1, so there's no mismatch. The same is true for index 1. However, at index 2, the original value is 4, while the sorted value is 1, which is a mismatch. At index 3, both values are 2, so no mismatch occurs. At index 4, we find another mismatch between 1 and 3. Finally, at index 5, the original value 3 does not match the sorted value 4, resulting in one more mismatch. Summing up, we find mismatches at indices 2, 4, and 5, giving a total mismatch count of 3, which is returned as the final result. The solution is implemented in the height checker method within the solution class. The problem asks us to determine how many students in the lineup are out of place compared to a sorted order of heights. First, we create a sorted version of the input list heights using Python's built-in sorted function. This gives us the expected order of heights. Next, we initialize a counter mismatch underscore count to 0. We then iterate through the original heights list, comparing each element with the corresponding element in the sorted list. If these two elements differ, it means the student is out of place, so we increment mismatch underscore count. Finally, we return mismatch underscore count as the result, representing the number of students standing in the wrong positions. The algorithm is efficient and operates in O, n log n, due to the sorting step, with the comparison loop running in O, n. This ensures the solution is optimal for the given problem constraints. This is the Java implementation of the height checker problem, number 1051, from LeetCode. The logic mirrors the Python solution. First, the input array is cloned and sorted, then we count mismatches between the original and sorted arrays. The Java implementation includes explicit type declarations and uses the arrays.sort method for sorting. The height checker method is the entry point, and the algorithm runs in O, n log n, due to sorting. In this example, we start with the input list of heights, 1, 1, 4, 2, 1, 3. The first step is to create a sorted version of this list, which gives us 1, 1, 1, 2, 3, 4. This sorted list represents the expected order of the heights if everyone were standing in non-decreasing order. Next, we initialize a variable called mismatch underscore count to 0. This counter will keep track of how many elements are in the wrong position compared to the sorted order. After that, we iterate through the list, comparing each element in the original list with the corresponding element in the sorted list. At index 0, both values are 1, so there's no mismatch. The same goes for index 1. At index 2, however, we find that the original value is 4, while the sorted value is 1, so we increment the mismatch count to 1. Similarly, at index 4, the values are 1 and 3, and at index 5, the values are 3 and 4, leading to 2 more increments. By the end of the iteration, the mismatch underscore count is 3, which means 3 elements are out of place, and that's the result we return. Now, in this second example, the input list is 5, 1, 2, 3, 4. Again, we start by creating a sorted version of the list, which results in 1, 2, 3, 4, 5. This represents the expected order. We initialize the mismatch counter to 0, and then proceed to compare each element in the original list with the sorted list. At index 0, the original value is 5, but the sorted value is 1, so we increment the mismatch count to 1. At index 1, the original value is 1, but the sorted value is 2, leading to another increment. This pattern continues for every index, as none of the elements in the original list match the expected values in the sorted list. By the time we finish comparing all the elements, the mismatch count has reached 5, meaning every single element is out of place. As a result, we return 5 as the final output. In the third example, the input list is 1, 2, 3, 4, 5. We follow the same process by first creating a sorted version of the list, which remains 1, 2, 3, 4, 5, since the list is already in order. Then, we initialize the mismatch counter to 0. As we compare each element in the original list with the corresponding element in the sorted list, we find that all elements match exactly. At index 0, both values are 1, at index 1, both are 2, and so on through index 4, where both values are 5. Since no mismatches are found throughout the iteration, the mismatch count remains 0. This tells us that all elements are already in the correct order, so the function returns 0 as the final result. To analyze the time complexity of the solution, we start with the sorting step. The sorted function in Python uses the timsort algorithm, which operates with a time complexity of O n asterisk log n. Here, n represents the number of elements in the heights list. After sorting, the next step involves iterating through the original list and comparing it with the sorted version to count mismatches. This comparison involves a single pass through the list, which requires O n time. When we combine the time complexities of these two steps, O n asterisk log n for sorting and O n for iteration, the dominant term is O n asterisk log n. Thus, the overall time complexity of the solution is O n asterisk log n. Now, focusing on space complexity, we observe that the sorted function creates a new list to store the sorted elements. This additional list requires O n space, where n is the size of the heights list. Beyond this, the solution uses a few auxiliary variables, like mismatch_count for counting and the loop index I. These variables require constant space, or O1, which is negligible compared to the space needed for the sorted list. Since the dominant factor is the memory used for the new list, the overall space complexity of the solution is O n. When comparing this solution to a brute force approach, the difference in efficiency becomes clear. A naive solution might involve nested loops, where each element in the heights list is compared with every other element to determine the correct order. This would result in a time complexity of O n squared. In contrast, the provided solution is far more efficient, achieving O n asterisk log n due to the use of sorting. Examining the best, average, and worst cases, we see that the sorting step consistently determines the overall time complexity. Even if the list is already sorted, the sorted function will still take O n asterisk log n to verify the order. Similarly, for randomly ordered or reverse sorted lists, the time complexity remains O n asterisk log n because of timsort's efficiency. The mismatch counting step, being linear, does not change the overall complexity. Therefore, in all cases, the time complexity is O n asterisk log n, and the space complexity remains O n due to the sorted list. Finally, let's understand the mathematical justification behind the time and space complexities. The solution relies on Python's timsort algorithm for sorting, which is a hybrid of merge sort and insertion sort. Timsort employs a divide and conquer technique, ensuring a time complexity of O n asterisk log n. The linear mismatch counting step, while efficient, does not dominate the sorting step, so the overall complexity stays at O n asterisk log n. On the space side, the sorted list is the primary contributor to memory usage. As it requires additional storage proportional to the input size, the space complexity is O n. This balanced approach of timsort and efficient iteration ensures an optimal solution for the problem. When working on this problem, there are a few common mistakes to watch out for. First, not creating a copy of the original array can lead to issues. If you directly sort the input array and compare it to itself, you'll lose the original data, which can make your solution invalid if the unsorted version is needed later. The solution is simple: create a copy of the array before sorting, using something like sorted_heights equals heights. Another frequent mistake is using nested loops unnecessarily. For example, comparing every pair of elements with two loops increases the complexity to O n squared, which is extremely inefficient. Instead, you can achieve the same result with a single loop that compares the original array to its sorted copy. Lastly, it's important to consider edge cases. For example, an already sorted array, arrays where all elements are the same, or arrays with just one element are scenarios that could trip up your code if not handled properly. Testing these edge cases ensures your solution is robust and reliable. Now, let's look at a couple more common mistakes. Using an unnecessarily complex sorting algorithm is one of them. Some people try to implement custom sorting methods or use less efficient alternatives, but built-in functions like Python sorted, or Java's arrays.sort, are highly optimized for performance, running in O n log n time. Sticking with these built-in methods is both simpler and more efficient. Another issue is confusing indices and values during comparisons. Remember, the problem is about comparing the values in the original and sorted arrays, not their indices. Accidentally comparing indices can lead to incorrect results. To avoid this, carefully iterate through the values in both arrays and count mismatches based on the values themselves, not their positions. This problem also offers some valuable insights that are worth noting for interviews. One key takeaway is recognizing the pattern. Many problems, especially those involving sorting or permutations, rely on a similar approach, comparing the original data to a sorted version. Understanding this pattern can help you tackle other problems more effectively. Interviewers also tend to focus on clarity and efficiency, so it's important to use an O(n) log n sorting algorithm followed by a single O(n) comparison loop to maximize performance. Additionally, discussing edge cases is a great way to demonstrate your thoroughness. Be ready to explain how your code handles scenarios like empty arrays, arrays with identical elements, or pre-sorted arrays. Finally, if you explore alternative approaches, such as using a hash map for frequency counting, be prepared to discuss the trade-offs. For example, a hash map might reduce sorting time but increase space complexity, so understanding these trade-offs shows depth in your problem-solving approach. There are also related problems that share similarities with this one. For instance, LeetCode 1122, Relative Sort Array, involves sorting based on specific rules and requires careful array manipulation. Another example is LeetCode 121, Best Time to Buy and Sell Stock. While it's not a sorting problem, it involves scanning arrays efficiently to identify patterns, which is a similar skill. As for alternative approaches, one option is the frequency counting method. Here, you count the occurrences of each height, reconstruct the sorted array, and then compare it to the original. This can reduce the need for sorting but requires additional space proportional to the range of heights. Another approach is the two-pointer technique, which simplifies comparisons by simultaneously iterating through the sorted and original arrays. However, in this problem, a single loop is often sufficient. Finally, while implementing a custom sorting algorithm, like quicksort or mergesort, can demonstrate your knowledge of sorting, it's generally impractical in an interview unless explicitly required. Built-in methods are usually the better choice. Thank you for joining this session. We reviewed the height checker problem and explored its solution, highlighting key concepts like sorting and mismatch analysis. Remember to practice similar problems to strengthen your skills. Don't forget to like, subscribe, and share this video for more content. Until next time, happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!